Hello there! Today we're going to be talking about the second part of the fundamental theorem of calculus. In plain terms, the second part of the fundamental theorem says taking the derivative of an integral produces the integrand. Taken together with the first part of the fundamental theorem, this says that differentiation and integration are inverse operations. I know what you're thinking. Disembodied radio voice, what kinds of problems am I going to see that involve the second part of the fundamental theorem? What a good question! Most FTC2 problems ask you to take the derivative of an integral whose upper limit of integration is an expression involving x's. Since the upper limit of integration in the second part of the fundamental theorem is regular x, this means we're going to have to use the chain rule. It's not as hard as it sounds. Start by defining a function that's almost the same as the one that we are given, except the upper limit of integration will be regular x. We'll then re-express our original function in terms of this new function, and then take the derivative of the new function. Of course, steps are meaningless outside of the context, so let's take a look at a few examples. Our first problem gives us the function g of x, and g of x is equal to the integral from 3 to x squared of 7e to the t dt. We are asked to find the derivative of this function. Seeing that x squared is the upper limit of integration, this immediately smacks of the second part of the fundamental theorem. Of course, in the FTC2 definition, we have an upper limit of integration of x. This means that this problem is not going to be a direct implementation of the second part of the fundamental theorem. In other words, g prime is not going to equal 7e to the x squared like the FTC2 might lead us to believe. So what are we to do in this situation? Well, we do like we do so often in math, we make pretend. We start by defining a new function that's almost identical to g of x, except its upper limit of integration is regular x. And in this way, we'll be able to take advantage of the conclusions from the FTC2. We'll call it a of x. This means a of x is equal to the integral from 3 to x of 7e to the t dt. There is a clear relationship between g of x and a of x. G is the composition of a and x squared, or if you prefer, a of x squared. This question doesn't want g in terms of a, though. It wants g prime. And remember, g prime is just another way of saying take the derivative of g of x. We write this as d over dx of g of x. And now we can substitute. G of x is, as we said, a of x squared. What a fascinating turn! If we are trying to take the derivative of this, we need to use the chain rule, where the outside function is a and the inside function is x squared. To use the chain rule, we take the derivative of the outside, evaluate it at the inside, and then multiply by the derivative of the inside function. The derivative of a is a prime, evaluated at the inside would be a prime of x squared. Derivative of x squared, of course, is 2x. The second part of the FTC tells us that a prime is equal to the integrand 7e to the x, which means a prime of x squared is 7e to the x squared. And then we multiply by 2x, because all we did was substitute. When we combine these two terms, we get 14x e to the x squared. This is our derivative. It may seem like magic, but all of the math is legitimate. To review, for a problem like this, you start by defining a new function that's almost the same as the function that you're given, except for your upper limit of integration is regular x. Redefine your original function as the composition of this new function and whatever your upper limit of integration is. In this case, g of x was equal to a of x squared. You then take the derivative of this new composite function, and that will give you the derivative you seek. Let's take a look at another different example. The next problem gives us m of x, and m of x is equal to the integral from 2 to sine of x of 1 over t cubed plus 7 dt. We need to know what the derivative of m of x is. Once again, this problem should remind us of the FTC Part 2 except for the fact that our upper limit of integration is an expression involving x. This means we're going to have to use the same strategy as we did in the previous example. Let's get started. We start by defining a new and almost identical function a of x. And a of x is going to equal the integral from 2 to x of the original integrand 1 over t cubed plus 7 dt. Now we redefine m of x as the composition of a of x and its upper limit of integration. In other words, a of sine of x. The problem asks us to find m prime, and remember m prime is equal to the derivative of m of x, or d over dx of m of x. Substituting is going to show us exactly what we need to take the derivative of. We need to do d over dx of a of sine of x. So many ofs in this problem. Again, we have a chain rule. This time our inside function is sine of x. The chain rule says derivative of the outside evaluated at the inside times the derivative of the inside, which means d over dx of a of sine of x is going to be derivative of a is a prime evaluated at sine of x for this chain rule times the derivative of sine, which is cosine of x. A prime, according to FTC2, is 1 over x cubed plus 7. We plug in sine for x, and this gives us 1 over sine cubed plus 7, and then we have times cosine of x. A little bit of reorganization is going to go a long way in making our answer look more palatable. In the top, we're going to get cosine of x, and that's going to be over sine cubed of x plus 7. And there you have your answer. Perhaps as we've been going along, you've noticed that this is actually not too far off from the standard fundamental theorem part 2. Our final answer still involves plugging in our upper limit of integration to the integrand. The main difference here is that we need to multiply our integrand by the derivative of the upper limit of integration. Maybe you're wondering, can I save myself the effort of doing all of this differentiation just by plugging in my upper limit of integration into the integrand and multiplying by its derivative? Good news! The answer is yes, you can absolutely do that. Because of the way that a of x is defined, we're always going to be plugging in our upper limit of integration into the original integrand in the problem. And thanks to the chain rule, we're always going to be multiplying by the derivative of that upper limit of integration. So have at it. For problems like this, you can always plug in your upper limit of integration into the integrand and then multiply by its derivative. And that is it, ladies and gentlemen. That's everything I need to tell you about this type of problem today. Thank you all for coming, and we will see you next time!